November 28th in Cambridge, Massachusetts. Welcome to the Picture Language Seminar. We're very pleased today to have David Evans. He's Professor of Mathematics at Cardiff University in Wales. He's visiting us for a couple of weeks. And he's going to tell us about quantum symmetries, which fits into his well-known work on subfactor theory and other aspects of mathematics. So David, we're very much looking forward to your talk.
Okay, thank you very much for the invitation to be here again, the opportunity to see much more of Arthur's group. So let me share the screen. Okay, so I want to talk about quantum symmetry from a couple of aspects. So the first, of course, goes back to the work of Von when he introduced the subfactor theory, which became a framework for looking at quantum symmetries. So symmetries beyond what you can construct from groups or even quantum groups definitions. Such things, loop groups. So that's subfactor theory. And so I worked for a long time with Matthew Gill. So that was one aspect of quantum symmetry. Then the other one is the relation with K theory. So in particular, the relation between conformal field theory and K. So I first became aware of this when I heard Dan give a talk at Imperial College London for the Congress in 2000. So shortly afterwards, I invited Constantine down to Cardiff. We spent a couple of days. And from that, it came this work with Terry, Andreas Aaserud, and Corey. So if you look carefully at the picture of Ulrich, on his shoulder on the right is Constantine. So Hopkins and Teleman is always in the background here. So okay, so subfactors and K theory. So the connection with conformal field. So the fundamental object in conformal field theory is, say, the Verlinde ring of one chiral half of a full conformal field theory. So mathematically, you can think of it as coming from, say, the representation theory of a loop group at some level. And in the subfactor theory, that they arise as bimodules for subfactors and factors, or the representation theory of conformal nets. So where you say associate a von Neumann algebra to, say, subsets of a circle, how they combine with representation theory of that. It is the Verlinde ring. And then, of course, from Hopkins and Teleman, we also think of it as through twisted equivariant K theory. In particular, from an operator algebraic point of view, that means you have some bundles of compact operators over your group, equivariant, and then the space of sections of that is considered, you take the K theory, that produces the Verlinde ring. Okay, so that then leads us to trying to consider higher twists, which is one of the main things I'll talk about today. So these are this is replacing the compacts with more exotic algebras, taking the corresponding equivariant bundles, computing their and then all this then provides possibly new tensor categories, fusion modules, and possibly new conformal field theories. There's always this underlying problem. If you have a modular tensor category, does it arise from conformal field theory as in double Vogel? So So that's one thing, and then the other thing I want to look at is actions of these tensor categories on various algebras or operators, just as you would with regular symmetries. With, say, a group, you'd be worried about what group actions occur on a particular operator algebra. So here we worried about actions of tensor categories, either as modules, which is probably more appropriate for K-theory picture, or as bimodules for the subfactor picture. Right, so I want to review some of the subfactor theory before I get on to the K-theory. So in the subfactor picture, we have, first of all, a fixed factor n, and on that we fix once and for all a system of endomorphisms, which is non-degenerative, braided, and such things. And then you look at inclusions. So that's fixed, n and its system of endomorphisms is fixed. And then you look at inclusions, you vary possibilities of putting n inside a bigger factor, which is related to the original system in this sense here, that I've kind of mixed my metaphors here between endomorphisms and bimodules. So if you have an endomorphism, you can construct a bimodule by twisting the action on one side. As in AXB is a X twisted with the endomorphism on the right hand side. So endomorphisms give rise to bimodules, and in these algebras in quantum field theory, that's all that can happen. In other words, every module arises from such an endomorphism. So you can switch back and forth between endomorphism by module pictures. So okay, so the inclusion has to be related to the original algebra in this sense here. I can either think of it by taking M as an NN bimodule.
It's better to point to that screen.
Okay. Yeah, that's true. So M as an NN bimodule is basically inside the system, or at least the sum, irreducibles from there. So that's what I mean by a braided subfactor, a system of endomorphisms on M, which is, say, braided, and a subfactor which is related to this thing. And then from this we could do the following. We could construct modular invariants. So in particular, we can induce endomorphisms from N to endomorphisms on N. This is like Mackey alpha induction. Mackey induction. This is George Mackey. So in group theory, you induce representations, but because you're really in the world of symmetry categories, you don't see the need for having two kinds of inductions. So here we have to use braiding to induce, but braidings come in pairs where you just reverse all the crosses. So there's two inductions, two ways of extending endomorphism from the small algebra to the big algebra using the induction. And then you look at this. You look at this in a product of alpha plus and alpha minus. That's basically taking alpha plus and alpha minus, decomposing into irreducibles, and counting the number of common multiplicities. So that's what you need. That's what you get in this section. So in general, the image of alpha plus and alpha minus are not even commutative, they're not graded. But the intersection is graded. So the extended system has a Verlinde ring, we call it, which is inside here. And that's all this inner product sees. So this theory of graded subfactors gives you modular invariance. Of course, there's always that problem. You've got a concrete modular invariance, and how do you find the subfactor, which realizes that, and so on, whether every modular invariant is realized by a subfactor. Okay, there's more structure here. I took the intersection and also look at everything induced by plus and minus. That's what we call the full system. That's MM. There's also an NM system where we look at endomorphisms from N to N, from N to N, which you can construct in this way, decomposing all these things into reducements. Then, in a natural way, the original Verlinde acts on this system here by multiplication. And these give graphs, and that's then the graph which recovers the classification of Capellian systems invariant for SU2 in particular. So they classified SU2 modular invariants with an AE classification. And it's these graphs here which recover Capellian systems invariant. Okay, and then so that's the role of the NM system, the MM system, which you get from using everything in sight. You can think of the multiplication here as thinking of this as a modular invariant, which also, maybe I should have said what I meant by a modular invariant, but that's just a matrix which commutes with the natural construction and action of SL2Z because of the gradient. If there are characters, as in the conformal field theory, that representation of SL2Z will transform the characters. But in general, you don't know whether you got these characters, and that's part of the problem of going from modular tensor category to a conformal field theory is to construct characters which transform the problem to your SL2Z representation. Now, this is a modular invariant because it also comes with SL2Z, but it's not usually normalized. So you decompose it into, it can be decomposed into normalized modular invariants. Okay, so that's a rough outline of subfactor approach to conformal field theory. And I've described it in terms of induction. You can also go back by restriction from here to here. These give you branching coefficients, and that's this picture here. Now, I think this was probably the last piece of work I did with Jens, which summarizes everything. So if you have N with a system of endomorphisms, then that may come from a conformal net, which has locality in the sense that algebra is associated with disjoint intervals, commute. Now, on the big algebra M, you also have nets of algebras, but in general, you don't have locality. So what we did, so that this is parallel to more side, we can find intermediate subfactors which do satisfy locality. And that's what we really need to get the modular invariant. So the M plus and the M minus have two induced Verlinde rings. They're identified by this map beta from one side to the other. The modular invariant looks like that. There's a description in terms of two-dimension. That's here. And the map from here to here is described like that. Okay, so that's probably a too fast introduction to subfactors and conformal field theory. So much of what I said has been summarized here in two collaborations with Aaserud. So the first one is very old, it's 98, so that's before alpha induction. What I've said about alpha induction is summarized in this recent paper, which appeared, I think, last month in the bulletin dedicated to one. So that's Aaserud, the young man, that's Aaserud today. Right, so this survey also has something on the K-theory story, which is what I want to get into. Okay, so from Dan and his collaborators, we know that there is this K-theory picture for the Verlinde ring. So I want to relate that to what I said already. So as rings, the representation of the loop group at some level is given by what I've written on the right as equivariant K theory, or G acting on itself by conjugation with some twist. So for us, that means non-trivial bundles of compacts over the group, equivariant for conjugation action downstairs and some action upstairs. Right. Then we take this space of sections and fixed K theory, and in that case, the Verlinde ring. Now, this is already interesting for finite groups because it helps explain where the conjugate action comes in. So if you've got a subfactor, you can always do a construction to get its quantum double, which generalizes Drinfield's construction of one from the group to quantum double of the group. Right. So if I want to take the double of this trivial inclusion over, say, hyperfinite factor R in an action with G, then Izumi showed that the correct quantum double is just this inclusion here, where I take R tensor R and take the product action of G on G, and then the diagonal action of G and G cos G. So that's the double. What I really mean by that is if I take this inclusion and compute the AA system, that recovers Drinfield's quantum double. You can be more specific. Instead of looking at A, B bimodules, B, B bimodules, and so on, you can switch to a picture of vector bundles, equivariant vector bundles. So this is due to Kosaki Yamagami. So in this way, all the bimodules inside look like equivariant bundles of G cos G, and in particular the AA ones are the ones on here which are equivariant with G on the left and G on the right, both acting diagonally. Right, so the picture for the quantum double is G cross G, G on the left, G on the right, diagonal. I can simplify that a bit because let's say I take the right action of G on G cross G, I can kill the second factor. And then I forget about that, the rest of it. I've only got left G acting on the first factor. And if you follow that through carefully, what you end up with is conjugation action. Right? So it's then natural that the K theory of the double is given by looking at this. Right? So that's what I mean by here. Of course, it's also with twisted. The twisted aspects we have. 3-4 cycles. So, okay, so that's the free Hopkins Teleman picture. Right, so then in this body of work, after Constantine visited Canada, I worked with Terry Gannon for many years. This project where we try to understand everything about the subfactors through K theory. So for loop groups, doubles of finite groups, lattices, and so on. And so for example, a matrix like modular invariant, modular invariant, it is a map from one K group to another K group. So that means it should be understood as subspecial KKL. So the modular invariants, the maps between K groups or even alpha induction and restriction should all have K theoretic descriptions. So that's what all this is about. And our byproducts, it gave some reconstruction for the test shows. So some reconstructions of conformal field theories from just a modular tensor category. The Tabariyama-Gami part is useful for the building blocks in the double of the whole. That's still to be completed. Okay, now I said I wanted to look at actions of symmetries, or quantum symmetries on particular operator algebras. So this is another way of looking at what free Hopkins Teleman did. So they were representing the Verlinde ring through the K theory of a particular C-star algebra. So, but maybe that's not the only way to do it. All right, so what we did was to construct C-star algebras such that when you took these modules, you recovered the tensor category. So in other words, you categorify the fusion ring that you start with C. So this is the construction of finding C-star algebras whose K theory recovers the ring, and we have this description of the tensor category as certain bimodules, certain modules. So in particular, this works for Pennig, Jones category. One thing I always intended to do, but never got probably around considering, is that we know from it is temporally deep thing that you can go to the Verlinde algebra by taking certain cosets. So that possibility is still open here. You could somehow use these inclusions of different PKs. Take some kind of coset to recover actions of the Verlinde algebra. Okay, now there's another way of looking at this. Is instead of thinking in terms of modules, I want to look at bimodules. So suppose I have a tensor category C, and then I look at all the dimensions, possible dimensions of objects, and then construct this finite group coming with an order So for example, I can take the whole group system, which has 6 irreducibles in these fusion gates. And there's a group part which just gives dimension 1. But this row satisfies cubic quadratic relation. The dimension squared is 1 plus 3 times the dimension. So that's this relation here. So the possible dimensions here are related to theta on the identity, and so I get this. But I think of it as an ordered group inside of the grids. Right, so then I can ask, I take all possible C-star algebras which has this K0, but maybe a non-trivial K1. And an example of that is the irrational rotation algebra for this rotation under theta. Right, so in work in progress with Corey Jones, which is not completely written down, we think we can construct actions of the whole group system and its value on the irrational rotation. And also categorifying this product here, because this makes sense because of this quadratic relation.
So is this related to a conformal field theory?
Maybe I don't know. No, that's any understanding of overall. Maybe I don't know. So it's based on the construction with George, who I think is in the audience. A long time ago, about understanding A theta as an effective evidence on circle algebras. So it uses that explicitly. Okay, so that's modules and bimodules. Now, I want to get on to these higher twists. No more time. It's okay. Okay, so three Hopkins Teleman is about bundles of compacts. Now you can push in one direction by looking at bundles of stable algebras A tensor K. It's more useful to have algebras A which solve themselves, not just as a straightforward isomorphism, but as in a very strong way, stronger than what is indicated in that line there. These are called strongly self-resolving algebras. Okay, you take one of these algebras, you consider their bundles over some space. And what Dadala and Pennig did just over 10 years ago is to describe this using some heavy homotopy, heavy homotopy to get this description. So this goes much further than Dixon duality with H3. So because it uses the homotopy theory, it's not very constructive. If you start with something on the right, what can you actually realize on the left? So that's one thing we've been looking at, but more in the context of actually throwing in not just bundles, but equivariant bundles. Right? So we're now going to look at the very specific SUN equivariant bundles for some particular algebras A, which are going to be these infinite tensor products. This F is going to be the generalization of the level. So F is going to be thought of as the twist or the level. Right? So a twist is going to be a map from finite dimensional vector spaces to themselves, which is exponential. It takes sums to products. Right, so maybe the most basic example is determined to take the top term to symmetry. Powers. So that's one dimension. The more interesting one is this the algebra description where you take all the antisymmetric points. I can't take symmetric numbers because I would end up outside finite dimensional spaces. Maybe there's another theory. Okay, so this level is what Hopkins Teleman really is, and this is these kinds of extensions of what we can do. So the one dimension, because in this case, if f of c of n is one dimension, then the UHF is completely trivial. It's just complex numbers. So you're back to bundles of compacts. Okay, now we're going to use bundles over this group out here. So it looks a bit messy, but I think of this G, Z1, Z2 as narrowed in Z1, Z2, Z1 to Z2 labeled by G. If you think of it that way, you sort of figure out what the picture is. And then there's a map where I just forget the Z's and go to G. And for the conjugate action, these are equivalent group outs. So that means I don't really think about G and G, I think about G and this Carl G. This is very similar to what I had before. I have G cross G, with G on the left and G on the right. So it looks as if I made things more complicated. But it allows you a richer structure because in the finite group case, you can, if you start thinking of G and G, if you think of G on the left, G, you can change that to different subgroups of G. So that it's a richer picture when you make things more complicated. So we want to look at bundles of these UHF algebras. So these are infinite tensor products in certain matrix algebras. And I have to say what lives over this point of the group point. It's this vector space, which is some of eigenspace, is tensor UHF. Now, in the say in the Dixon-Duarte theory, you think of twisted K theory as being locally trivial bundles, but on the overlaps, you join them by automorphisms of the big algebra. So instead of working with automorphisms, we're going to look at the equivalent picture of bimodules. So instead of thinking of automorphisms, we're going to look at MF bimodules. So I can easily act MF on the right, but how do I act it on the left? So to do that, I can decompose the entire f of c of n like this, and then I can, in m of f, I can always pull out any one of the factors, which is not what I've done here. I've taken out a part of it. If I have an infinite tensor product of matrices, each of which is 2 by 3, I can pull out, of course, M6 or M2 times 3, but I can also pull out 2 by 2 matrices. So if this is an infinite tensor product of 2 times 3 matrices, that's 2 by 2 matrix. I can pull it out again. So because of this picture, I can act on this on the left and on the right. So I've got bimodules to help me consider. Then we have this picture here. So it's the K-theory of these algebras you were interested in. Okay, so just as in theory of mixed mutuality and free Hopkins Teleman, we have bundles on spaces locally trivial, something happening on the overlaps. And trying for the picture there, so for this is for SU3, that's the maximum torus of SU2. Here we would need three things to overlap. Now, locally, everything's going to be trivial, so it's just regular. The algebra sitting above local space is just going to be this infinite tensor product with the SU2 action. As said, well, SU8. So locally, this is what I mean. And then the problem is how do we glue them together? So you can easily compute the K-theory or the equivariant K-theory of SU2 acting on the symmetries. It's just this ring here, rho being the irreducible, the fundamental irreducible. Okay, so the classical case is this. In that case, there's no complication with RF, R, they're the same. And then the K-theory is described by this picture here. The rows correspond to irreducibles here. And the one you killed here, the one you got. That's first result. Now, and Mike Hopkins and Constantine. Okay, so we can do something similar, but it's it now gets it's described by the representation grid of the local part killed by an ideal generated by one element. Okay, but it's different in some senses because this is not the representation grid of SU2, it's representation of SU2 localized at a certain place. So that's one thing, and then the polynomials that appear for this twist here, which is this looks like this. And the most interesting examples are with K's out. These are the polynomials that appear. Now, there's a couple of simplifications in this case. When K is odd, you can show that localization is not necessary. Because the ideal you're generated killing out by helps kill the localization. So in that case, in these odd cases, it's the representation ring of SU2 divided out by basically these things here. And then you do get fusion rings, which I've described like this. This is basically SU2 after levels, even levels. but I don't know if that's a coincidence, because we cannot see a similar function for higher SUN. Okay, so this year we extended it. So previously we've done it for SU2 and SU3, and now we're doing it for all the SUNs. And again, it's given by these localized rings, divided by an ideal given by 700 checkpoints. So for SU3, you can either think of the ideal as being given by things which kill these things coming down here, or just two coming across here. So it's the two coming across that we've got in the picture here. So these are really, in terms of the language of polynomials on the maximal torus, which are invariant under the Weyer group. So that's a description of the equivariant K theory of these higher twists. And for SU2, we could compute it exactly. For SUN, we have this Q coming in here. So we only do it over the rations, because in the spectral subspace computations, we have to use at various points, averaging by Weyer groups, so on. So that means you're dividing up setting integers, and that messes up the integral computation. So the proof is for over the rations, but we believe that as for SU2, it's correct over the integers. Okay, so that's one part of this. Now, there was a description by Gannon of these Verlinde rings in terms of a single potential B. So when you divide out by that ideal, you can construct it by finding a potential B such that when you take all the derivatives, you do the same thing as you did before. And that helps understand some geometric description of the Verlinde ring. Now, for us, we can also do that. We can find the potentials which generate a fusion ideal. Now, Gannon also compared the Verlinde ring computation with this chronological ring for Grassmannians. But his comparison was by computing the two things separately and observing that they were essentially the same. Witten wrote a paper trying to understand that more conceptually. It's on the physical side with functional integrals and so on. So I think there's still, from an operator algebra point of view, a lack of understanding between this, especially now higher twists. In the classical case of free case, you're talking about determinant functions, so that's completely wrong. And of course, also if you look at Presley Siegel's book on root groups, determinant functions are every classical twists. Okay, now that's for SUN. You can be a bit more specific with torus sections. So I mean, a single torus, and I think of the following: I construct a UHF algebra, infinite tensor product V, which is carries a representation, finite dimensional representation. So now, because of well, the following, if I take a character of that representation, it really should have positive and negative powers of t. Right, but I can always multiply my representation on V because I'm taking the adjoint action with NV. I can always multiply it by a very high power of t. So that means that I don't need to worry about negative powers of t. It's enough to consider characters which only have positive powers of t, and that makes what I'll explain later easier. Now, what we can do is to show that the bundles, equivariant bundles for the circle on X for these UHF algebras tensor complex are described by this cohomology theorem coming from the arguments, the automorphisms, the tensor A. Now, to compute this cohomology theory, we need the coefficients, and they're given basically in terms of these homotopy groups of the unitaries on the fixed point algebra. D is an infinite dimensional matrix algebra. T is an action which leaves invariant all the finite dimensional subalgebras. So this algebra here is an inductive finite dimensional algebra, so it's easily understood. So the K-theory of this circle action on D is Z of TT inverse. That's the representation for the torus as a group, and then the localization. And the bit that's important is this pi1, which is described by K naught of dt. There's a map from the right. If I have a projection in the fixed point algebra, I get a unitary. If I have a loop, I exponentiate. And for these algebras, that's a nice notice. Now, the K theory of the fixed point algebra D of T is not the same as the equivariant. It's closely related. It's a smaller ring. Now, just given like this. It doesn't matter what it is, but it's really. But there's, I need two other subrings as follows. And the reason is the following. Okay, so if I want to compute pi1 of the unitaries in the matrix algebras, it's going to well, or even the hybrids. So suppose you take the gauge action of the circle on the Fermi algebra. So that means my P of t is 1 plus t. So it's a 2 by 2 matrix. I will take 1t, and then I'm taking a fixed point algebra under that action. And then you basically get Pascal's triangle. Now, and at each node in Pascal's triangle, there's a number, of course, and that gives you the size of the matrix algebra. Now, every dimension except the first and the last blows up as you go further down Pascal's triangle, but the ones persist forever. right? And so that means that the homotopy groups differ at the endpoints and in the middle. So if you've got these, if you've got this, that's if you've got something at the beginning. If you, this is the inverse. It's a messy way of going from the first point to the last one. So I've got to consider whether I've got these one-dimensional spaces or not, and that's all this is about, taking care of that. So, and then by this spectral subspace computation, we get this picture here. Well, and now, unlike the non-equivariant, the coefficients vary as you go along the sequence. So they're not. So that's what we have there, and just finish with this now. Yeah. Suppose we look at the simplest possible case where we have bundles of basically the compacts. Now, in that picture we have here, where we compute, we get H1 plus H3. That doesn't look anything like an equivariant computation, but it's there in disguise by the Coordinate description from here to there, which is then the what you would expect as equivariant Dixon-Duvalli. So there's still something to understand in the higher cases here, beyond the C tensor K, as something more like equivariant Dixon-Duvalli. Okay, so I think I'll stop there. Okay, thank you very much.
Well, thank you, Dan, for a very comprehensive talk. David, I was thinking of Dan for most quoted person in the lecture. But maybe, Dan, you have some comments.
No, I enjoyed it. Just I'm trying to remember, there was work of Constantine Teleman and Chris Woodward about higher twists. And I don't know if that's related to what you were doing.
I don't think so, but I shouldn't be too definitive about that. It should be too.
Yeah, I was trying to remember. I'm not totally sure.
What is your program?
Well, first of all, this is suppose we look at what we've done for SUN, high twist bundles for SUN. The computation is at the level of fusion rings, so there's still a question of understanding that to categorify that. So to understand the multiplication and the fusion sense of the system. So we think we can probably do that for SUN, but because we can use not just SUN, but you can use your whole family of SUNs. You can relate SUN across SUN with SU2N and use that. But we're looking now at G2. That's the rank 2 group, and you don't have that issue. So I think we'll be able to show that we'll be able to compute the K theory, but to categorify the multiplication will be much harder. Then there's also the question of, we focused here UHF algebras, but we also want to look at those algebras. If they're all to no infinity because they are strongly self-absorbing. And but OM bundles will also be interesting because well, they don't have the strongly self-absorbing. They do absorb UHF algebras, and the infinity algebras, but I'm still not sure whether they absorb these algebras equivariantly in the strong sense. So we want to do there.
Are there any other comments here?
Well, I was wondering,
Yes.
Can you hear me? Well, I've got two machines working. I'm sorry, but I was wondering if because it's the construction on page 10. If the rotation algebras were part of the was that an example of the B on page 10? There's the Caesar algebra that arose in connection with the
No, that's no. In the B's, when I wrote down the K theory of the B, it was only counting the rank of the fusion ring, whereas the
So can you hear me? I'm sorry, I'm a bit mixed up with my devices, but I just got a new iPhone. Okay.
this coming in.
I was just wondering, on page 10, you have the B, the algebra B with the same K0 as the category C.
Yeah, but
by the way, is that just a group isomorphism, or do you look at the order structure on K0 of B?
the order structure is there, but that K0C, I just mean the rank.
Can you hear me?
It copies and Z for the rank.
The trouble is, I can't hear you now.
Yeah.
I had to use
No, I think that the second half of the sheet is more detailed about the K theory. That I'm using the dimensions.
well,
The algebras in the first part, the B's, that they're just AF algebras. And I think the second part is a richer theory with more possibilities for the algebra.
Yeah. George, can you hear David?
I think it's trying something. Okay.
Tell him we can hear him. No, we can't hear him.
okay, so I'm connecting again. Can you hear me? I'm just wondering if on page on slide 10, the algebra B that arises is what properties that has. Is it always a simple Caesar algebra? And does the rotation algebra down below the A theta, is that a special case of the B?
Two completely different constructions, and the B's are never simple. in the.
I see. So what, are they type 1?
They're AF algebras, yeah.
Oh, they're
Yeah.
AF algebra. Okay. Well, I noticed that one of the titles of one of the papers mentioned at the end was about AF algebra. So is that the well?
No,
Okay. Anyway, it's a very interesting thing.
Well, thank you, George. Maybe you should continue the discussion offline.
Yeah. Right. Thank you.
Are there any other questions?
I have a quick question. So from quantum symmetry, you're able to relate to K theory. Now, are there related index theorems in this context? Did you hear my question?
Yeah. I'm not sure how to answer.
Thanks.
You know, in index theory is everywhere. You know, it's the dimensions. It's even the definition of Jones index is a K theoretic one. You take M, the big algebra is a modulo of the small algebra, and it's finitely generated and projective if and only if the Jones index is finite, and then that gives you an element of the K group, and that's the Jones index.
Yeah. So that's a decent invariant, but I'm thinking more in terms of Atiyah-Singer's index theorem
Yeah.
that tabulate all the topological phases, whether that's possible in this context.
Yeah.
Usually non-commutative geometry provides that route, but here do we have that option?
Yeah, I mean, I think you see much more of that in the world.
Okay. The other question is extending from K theory to Kasparov K theory. Is that possible in this context again?
Yeah, because the modular invariant, for example, or alpha induction are maps between two K groups. So by the UCT, they should correspond to KK elements. Then the question is, what special KK elements give rise to modular invariance? So
Thank you.
Are there any more comments? If not, let's thank David again for a very beautiful talk. See you next week.